Alright, so let's discuss a bit about Fourier transform and especially its use in infrared spectroscopy. When we talk about Fourier transform, first we have to understand essentially what's happening, the mathematics behind it. What we're doing is we're converting a time domain signal. That is, we see changes in signal intensity over time into a frequency domain signal. How frequently do we see those changes? Well, that's going to be our frequency. Right? So our x-axis is changing from a time domain to a frequency domain. In other words, x-axis changing from seconds to hertz. Now, that's not as simple as just doing 1 over our signal so that we get that difference, that conversion between the two. When we look at Fourier transform, here in this top image we have two different frequencies, the darker blue and the lighter blue. Hopefully that shows up well. This is from chapter 11 in our textbook. This is figure 11.6. At the beginning of this experiment, you can see again we're in the time domain. Both of these signals overlap very well here. Right? So this is overlap. You can see in the middle they are almost exactly opposite each other, right? And so here we have, here they're opposite. And here at the end you can see they overlap once again. When we talk about wave mechanics, of course, we don't use the terms overlap and opposite. We talk about constructive and destructive interference. And so if we took the sum of these two traces, we'd see that we have pretty good intensity, good power here at the beginning and at the end, where those overlaps lead to constructive interference. And we have power that's pretty close to zero here in the middle, right? This y-axis doesn't have any units, tisk, but here's our, more or less, our zero and our y-axis, on our y-axis, yeah. Right? And so, of course, when we are taking a measurement, our detector is no good at separating out what frequencies there are. They can only see the overall signal. And so if the overall signal is this combination of multiple frequencies, we have to come up with a technique to sort of undo those frequencies. And so that's where Fourier transform comes in. And so going from one to the other takes a Fourier transform. And we're going to abbreviate that FT. And so Fourier transform takes us from this time domain into the frequency domain. And it enables us to, it's essentially a mathematical way of taking a curve and several points along that curve and figuring out what frequencies have to be used in order to make up that particular interference pattern. And so we get out the two resultant frequencies. I use the term interference pattern. If you have talked in physics at all, you may have heard the term interferogram. That is another way of thinking about this. You know, we're taking some sort of snapshot, and so we have this interferogram, kind of like a chromatogram from a chromatography instrument, but it's an interferogram from an interference kind of measurement. Right. Now, we are not going to get into the math behind this. For those of you that have had or taking PChem, you're using MathCAD. MathCAD has a fast Fourier transform function built into it. And so, you know, this math is widely available and largely programmed into computational programs, and so we don't have to worry too much about it. Sorry for those math majors among us. So what are the benefits of Fourier transform, right? Why do we do this instead of having a monochromator, right? And so versus what we call a dispersive instrument, a monochromator instrument, it is much faster due to a multiplex advantage, right? Think about in UV vis, when we discussed diode array UV vis, we can take all of those wavelengths at once, right? That light is spread across that diffraction grating and then into each of those set of diodes. And so as long as we have enough diodes, we can take the whole spectrum at one time, and we don't have to scan our monochromator. In a FTIR versus a monochromator IR, also called a dispersive IR, we can take all frequencies at once. And so Fourier transform is able to pick out all the frequencies in a given sample, even if they're very close together. And so we don't have to disperse the infrared light into sort of wavelength ranges and then do Fourier transform. We can do the Fourier transform on the raw data and collect all frequencies at once. And so, again, this multiplex advantage is because we can collect all frequencies simultaneously. We also get much better signal to noise. Now, this is not necessarily a byproduct of the instrument or of the method, but this is just a throughput advantage. All throughput advantage means is that we can take more scans in a given amount of time. Right? And so this throughput advantage is very closely tied with the fact that it's faster due to that multiplex advantage, right? And so we can take more samples in less time. Right? Think back to our Chapter 5 discussion of signal to noise, where the signal to noise ratio increases by a factor of root n. And so, if we can do 100 averages in the time that it took to do one scan, we have a tenfold increase in signal to noise. And so, not only does it save time, but in the same amount of time, we get much better signal. The last is we actually end up with better resolution. The prisms that were made for dispersive IR instruments did not have great resolving power, and so the Michelson interferometer, which we'll discuss in the next slide, has a much better resolving power, and we're more able to see those small peaks or those closely neighboring peaks. Okay, and so what do the guts of FTIR instrument look like? The heart of an FTIR is the Michelson interferometer. If you talk in physics about Michelson-Morley experiment, it's likely that they'll discuss some gravitational waves or something a little more on the astronomical scale. But we use the Michelson interferometer in an FTIR to do very similar things. We need to create this interference pattern so that we can measure all frequencies simultaneously. And so we have, let's walk through this based on these letters here. We have, in A, we have our source, and we'll talk on Friday after our journal club about what kind of sources are used and things like that. And so from the source we have all frequencies. Like I mentioned in class on Monday, when we discuss UV vis, we talk about wavelengths. When we discuss IR, we talk about wave numbers. And when we discuss microwave, we talk about frequencies. And so because here we're going to talk about wave numbers in terms of frequency, I'll stick with the notation that's in the textbook. Here we have 3 frequencies, nu 1, nu 2, and nu 3. So we do have, of course, more than just these 3, but for the sake of this little diagram, we're only going to talk about these 3 frequencies. we'll track with A here and go to B. This B is a beam splitter, semi-transparent. It doesn't have to be a 50-50 beam splitter, but many cases it is. And so half the light goes to the stationary mirror, and half the light goes to this moving mirror, this pulsing mirror. I'm going to change colors here. Light leaving the source, we'll color in red. And so this is all leaving the source. And then light that's reflected back, we'll do in green. And so it reflects off that moving mirror, that pulsing mirror, and it reflects off this stationary mirror, and it recombines. Right now, when it hits the beam splitter, half that light goes back to the source and kind of gets thrown away. So part of that light dies. The other half of the light goes through to the sample, passes through the sample, through a second set of optics, and into the detector. Now, as that pulsing mirror moves, it moves with a known frequency. I'm going to call it a moving mirror. Our textbook is the only one that calls it a pulsing mirror, and that just sounds so foreign to me that I'm going to stick with moving mirror. And what it does is it creates this interferogram, but it creates the interferogram not for multiple frequencies. It creates the interferogram for each and every frequency with itself. Okay? These are from my lecture notes at Purdue when I was a grad student. In red, we have the light that's reflecting off the stationary mirror. In blue, we have the light that's reflecting off the pulsing mirror. This first one would be like a time equals 0, right, where the distance that the moving mirror is from the beam splitter is equal to the distance the stationary mirror is to the beam splitter. Okay. So when we're here at t equals 1, our moving mirror has not moved very much. The distance of the moving mirror from the beam splitter is equal to the distance from the stationary mirror plus just 1/8 of a wavelength, right? A tiny bit. And so we have 1/8 added on the way back, on the way there, and we have 1/8 added on the way back, and so that's an extra 1/4 of a wavelength that's been added. And so you can see here that we're shifted by 1/4 of a wave. At t equals 2, the distance of that moving mirror is now just a tiny bit farther out. It's the distance of the stationary mirror plus 1/4 lambda. And so we have a 1/4 lambda on the way to the moving mirror and a 1/4 lambda on the way back from the moving mirror. And so a 1/4 plus a 1/4 is a half. And so if we're shifted by half a wavelength, then we're going to get perfect destructive interference. All right? Perfectly destructive, so we have no signal. At time equals 3, the distance of the moving mirror is equal to the distance of the stationary mirror plus 3/8 lambda. So that's an overall shift of 3/4, and you'll notice that now it looks very similar to the one at t equals 1 in terms of the overall intensity and the overall interference, but just the two waves are switched with one another. Instead of the reflected wave being just a little bit behind, now the reflected wave appears just a little bit in front of the stationary mirror's reflected wave. In this particular example, this would repeat. At t equals 4, we'd be to the distance of the mirror. The moving mirror equals the distance of the stationary mirror plus a half lambda. A half there and a half back is 1, and so they would overlap perfectly at t equals 4. And so you get this overall change in the intensity of each frequency how quickly that intensity changes depends on the frequency of the moving mirror. This reference laser serves no purpose except to tell the computer where our moving mirror is relative to the stationary mirror. And so this reference laser, HeNe, so helium neon lasers have a wavelength of 632.8 nanometers, something like that. It's red. And so this reference laser goes out, gets split by the beam splitter, goes up to the moving mirror, goes to the stationary mirror, goes through the sample as well. It actually might bypass the sample depending on your instrument, but it goes through the optics into a detector. Now sometimes that detector is separate from the sample detector, sometimes it's not. In the instrument that we have at Wofford, the detector for the reference mirror is actually about here, right? It detects it just before it goes through the sample. But anyway, what that does is it creates an interferogram of just that HeNe wavelength, and based on sort of the intensity of that light source, it knows the position of that mirror in terms of fractions of wavelengths. So, once we do all of that business, we end up with this interferogram here, right? And so F is our interferogram. And that interferogram is of all the frequencies. We do this Fourier transform, and we get out the individual frequencies that pass through the sample. Right? And so just like in UV-Vis, if the sample absorbed a certain frequency, we would see less of it after the sample. If a sample didn't absorb a particular frequency, that intensity wouldn't change, right? When we look at FTIR, it's often, almost always displayed as percent transmittance. And so all the peaks in FTIR come from the top down rather than the bottom up. I think it's just a way to differentiate UV-Vis from IR when it's, being looked at, being published, so that you sort of immediately know, hey, I'm looking at an IR, hey, I'm looking at a UV-Vis, rather than trying to look at the x-axis, read the caption. It's a faster way of identifying one. So again, this Michelson interferometer works to create this power curve, and this power curve is created for every wavelength, right? So we get one of these. I should say for every frequency if I'm going to keep things consistent with the book. Right? Now the interesting thing is that we can take this power versus retardation curve. This is retardation of the moving mirror. So in other words, how far has that mirror moved? And this takes into account both trips, right? So it takes into account from the beam splitter to the moving mirror and back to the beam splitter. So you see that we get our peak here at one wavelength rather than at half wavelength. Because we know the speed of the moving mirror, we can convert this retardation x-axis into a time x-axis. And so we get power versus time. So we convert the retardation to time by knowing the moving mirror speed. And we know that both from the motor speed that's set by the instrument, but also by that reference laser, right? If our mirror is moving faster or slower than it should be, the reference laser will correct for that. Right? Once we have power versus time, so after we can do that conversion, right, we have power versus time, and then we take that graph and we do a Fourier transform, and we Fourier transform that into power versus frequency. So this Michelson interferometer is a pretty complicated piece of kit, in all honesty. Um, with the moving mirror, there's only really one moving part, but that one moving part throws a lot of wrenches into the works. We're going to take apart an IR next week in lab, and so we'll go through this explanation a bit more when we do that. All right, that's all I wanted to cover in this video. We will talk about the actual instrumentation bits and pieces, the sources, the detectors, and sample introduction on Friday after our journal club. Don't forget to look at that journal club article. Take care.